So thanks everybody for joining us for the NGRREC Intern Symposium. I'm Ted Kratchmer. I think I know almost everybody on the call today. Thanks again for joining us. And just before we get started, I want to say a couple things. One big thank you to the interns this year. Ashley, Alex, and Phil did a great job in challenging conditions, I would say. We're very happy to have all three of them join us this summer. Unfortunately, some of the things that we normally would like to do with our students, we're unable to do for obvious reasons. And that's regrettable, I guess I would say. But huge thanks to them for being willing to, I guess, take a little bit of a risk on spending a summer with us through the project and through their projects and through the program, and with our intern advisors, Liz, Justin. Thanks so much. We're very happy to work with you all and continue this work. And hopefully when things get back to normal, we'll be, of course, continuing these relationships. We're very excited. I mean, this is a program that we've done for many years. It's really a centerpiece of what we do at NGRREC on our education side. And over the years, it's really gotten us, really helped us expand our network and help, train the next generation of scientists and professionals in the environmental and river space. We have former interns that have gone on to do really good things, and we're very proud of that. And advisors and interns both make that possible. Also, the program is made possible through the Monticello College Foundation, who funds some of our internships every year. They've been a generous benefactor of the program over the years, and just want to say thank you to them, as well as Lewis and Clark Community College, our host at NGRREC, who over the years has generously funded these internships, as well as grant funding from the state of Illinois. So thanks to all who participate. And so unfortunately, Gary Rolfe, Executive Director of NGRREC, is unable to be with us today due to some family commitments, but he sends his regards. And I'd like to ask Dr. Jason Knopf to introduce his intern, Alex, and we'll kick things off here. The program, each presentation is going to be about up to 20 minutes or so, with up to 10 minutes of questions. And if you do have a question, please type that in the chat box, or at least type your name in the chat box and indicate you have a question. And Louise, who's going to be doing the controls in the background, will either unmute you or I can read the question, and we will go from there. So thanks again to everyone. And Dr. Knopf, I will pass it to you to introduce Alex. Thanks.
All right. Well, thank you, Ted. And before I get to Alex, I would certainly like to thank everyone who's been responsible for getting the internship program together and keeping it going. I mean, it's just, we all know how challenging things are right now, and I think, maintaining this opportunity has just been wonderful, and I really appreciate it. So Alex Swan has worked in my lab for the internship, and I'm just going to give you a little bit of background on him and then let him take things away. So Alex is heading into his junior year at St. Louis University, and he is a dual major biology and computer science, which made him a particularly attractive person to work in my lab because we tend to do a lot of computational informatics work. And so, you know, when he walked in my door last fall, I thought, you know, I wanted to play it cool, but, you know, really convince him to get into the lab. And so he started working last fall and then headed off to Australia for a study abroad program in the spring, but then was able to come back to the lab because of the internship program. And so for those of you who I haven't had a chance to meet yet, the work in my lab focuses on largely how humans impact freshwater systems and how, you know, changes to physical habitat subsequently impact ecological systems. And so one of the things that we're really thinking about is sustainability of freshwater systems in the context of climate change and what management applications we can use in that regard. And so one of the things we think about is water temperature and how do we keep streams and rivers cool. And one way that people think we can do that is by maintaining or improving riparian vegetation, which is the canopy overhanging and covering the stream or river. But we don't really have a great idea about how canopy cover can improve stream conditions, particularly in the context of changes in climate. And so what Alex has been working on is trying to develop methods to use online data to quantify canopy cover and then apply some information that you derive from those data to develop models to predict how water temperature will change as we increase or decrease streamside vegetation. And so, you know, I'll be honest, what I asked him to do this summer, I didn't think he'd be able to do, but he did it. And I'm just thrilled with how it worked out. And it's, you know, it's one of those projects where it leads to more questions. And I truly believe it's going to lead to us being able to do more things in the lab. So I greatly appreciate his efforts. And I'm looking forward to having him tell you about it now. So I'll pass it along to Alex. Thanks, Alex.
All right. Well, hey guys, I'm Alex. Before anything starts, I am unfortunately having some internet issues right now. So I think I will probably be having to turn off my video before I present. But with that being said, let's get into it. All right. Hello? All right. Can you all see this? Yes?
I can see it.
No?
Thank you.
Maybe
Yes.
so?
Yes, thank you.
All right, sounds good. All right, here we are. The relationship between canopy cover and water temperature in the Merrimack River watershed, AKA the story of my summer. It was a bit of a journey, but here we are, and I'm happy to share it with you guys. So for a brief introduction, water temperature is fundamentally important to freshwater species, ecosystem processes, and can also influence water quality. Ongoing climate warming is forecast to dramatically reduce the habitat area of cold water aquatic organisms. So in light of that fact, we thought we would think about how canopy cover plays a picture in this part of water temperature, and it could possibly in the future be used as a way to shelter water temperature. So our objectives for the summer were twofold. For part one, we were trying to explore relationships between canopy cover and water temperature in streams throughout the Merrimack River watershed in eastern Missouri. Part two was more of a computer-based approach where we were attempting to model water temperature in a section of stream to predict the influence of canopy removal or addition on stream temperature. Our study sites, you can see here on the map, 15 stream sites in the Merrimack River watershed in eastern Missouri. They range from about a 45-minute drive to about a 2.5-hour drive away. Each site had a temperature logger collecting daily data for 1 year. Those are daily average temperatures from 1 year. So, getting started here with part one, canopy cover and in-stream water temperature. Here we have two of the study sites, LaBarque Creek and Huzzah Creek. And as you can see, one is sort of sheltered, one is sort of open. the big question, of course, is there a difference between those two in the in-stream water temperature? So first, we had to find a way to quantify water temperature sensitivity. This is how we did it. We used a linear regression on daily water and air temperature for the 1 full year. So this is one of our study sites, Big River, and each point is the average daily water and air temperature for 1 day out of the year. So the slope of the linear regression here, 0.9, shows that on average throughout the year, when air temperature went up 1 degree Celsius, water temperature went up 0.59. So a lower slope would be a more insulated river, and a higher slope would be a less insulated river. And as you can see at the higher and the lower ends of the temperature spectrum, the relationship sort of breaks down. And this becomes more apparent when you divide the year up into different seasons. So for spring and fall, we have relatively very high correlation values and relatively higher regression slopes. This is because during the spring and fall, the water and air temperatures are rising and then falling together, so you get a very nice diagonal line. But in the summer, they just sort of stagnate and you get a cloud, so you can't really run a regression on that. And then in the winter, of course, air temperature can fall far below 0, but water temperature must stay pretty much at 4 degrees Celsius or higher, so you get more of a flat line. So for, going forward, the slope of the spring temperature regression will be one we use to quantify water temperature sensitivity, along with maximum weekly water temperature as a measure of temperature insulation. So for estimating canopy cover was estimated 1 kilometer upstream of the temperature log grid at each site. The first thing we did was we devised a remote canopy cover estimation technique on Google Earth, which was based on a technique in a paper by Ukar et al. 2013. The purpose was to begin developing a less field-intensive method of estimating canopy cover. So the method used regular grid point sampling over satellite imagery of the river area, obviously obtained using Google Earth. And our regular grid points were spaced 4 times 10 to the negative 5 decimal degrees apart. That comes out to about 4 meters. So the canopy cover then is the points which fall on canopy divided by the total number of points, which at an average of 474 points per site is a lot of counting. So here's an example of how it works. This is one of our sites, Boone Creek, and as you can see in this little zoomed in section, here are 8 of our points, and if I was going through counting this, I would say probably 7 out of those 8 fall on canopy. Maybe just that bottom right one wouldn't. So after that was done, we then used a convex spherical densiometer to estimate canopy cover in the field. It's a funny tool, a convex spherical densiometer, basically just a little box with a mirror in it. The pictures actually have a concave spherical densiometer, but the convex one is very similar. The mirror just goes out instead of in. So 10 measurements were taken by 2 observers at each site, 1 per 100 meters. You look at the mirror, it shows up what's above you, and you can quantify how much canopy there is. So each measurement was 4 densiometer readings at 90-degree rotations to get a full picture of the area you're standing in. Densiometers are a time-tested standard for field canopy measurement, and they date as far back at least as the 1950s. So to figure out if the Google Earth method has any viability, we must first see if it agrees with the densiometer estimations. So do they agree? Well, for a first pass at the agreement, we used a Spearman rank correlation, and we found that there was a strong positive monotonic relationship between the 2 measurements with Spearman's correlation coefficient of 0.817, so that's pretty good to start off with. But we must then test for bias and variability. So we did this using a method described in Bland and Altman 2010. So here on the y-axis, we have the difference in the estimation. That's just the densiometer measurement minus the Google Earth measurement. And we've marked here on the graph the mean. So as you can see, the mean difference in the measurement is pretty high. It's about 6.5%. And the variability is also pretty high. You add 2 standard deviations and you get from about 25% difference to about negative 12% difference. So that's not a very good sign. It shows that maybe they might be measuring different things. There's a consistent bias. And also the measurements from the Google Earth method are pretty variable. But there is still hope. If you strip away all of the imagery dates, except for only the Google Earth images that are on the most fully leaved summer estimates, So maybe if you had some in May, the canopy is just a little bit less than full, or September just thinning a little bit. You take all that away and you just go with June, July, and August, then you get a very good agreement, and you greatly reduce the variability in the differences between the two estimates. So this is pretty promising. However, obviously, we only got 6 sites with these great summer images on Google Earth. So the biggest problem here is the lack of imagery. 6 out of 15 sites, not a very good win loss there. So back to the main thrust of part 1, canopy versus temperature sensitivity. No correlation was found between canopy cover and water temperature sensitivity or maximum water temperature. Neither of those showed any correlation whatsoever. As a guess, this might be because other factors such as flow volume and 1,000 other factors likely obscure their relationship. Canopy cover certainly does affect temperature. Of course, it blocks incoming solar radiation, but these results suggest that it may have no predictive power in this area. So if you're driving along in the Merrimack River Basin and you see a nice stream that looks very nice and shaded and it looks very cool, what this says is that canopy cover does not predict the temperature of the water at all. So it might be warm water, it might be cool water, you don't know. So on to part 2 of the summer, stream segment modeling. The model we used for the stream segment modeling portion was SSTemp, which is a simplified version of SNTemp, which is a model designed by Fred Thurrer and others in 1984. And despite debuting in 1984, it's still a gold standard for stream network modeling. The issue with it is it's not used very often because it's extremely complicated and requires many, many variables. So in light of that, SSTemp was derived from SNTemp in 1990 by John Bartholow, simply for ease of use. It calculates stream temperature as a result of 8 positive and negative heat fluxes. You can see them there. Obviously, the one we will be varying is streamside vegetation or shading. And what SSTemp does is it outputs mean, maximum, and minimum temperatures in one section of stream for one single day. So our study site will then be one section of stream and one day. We will be measuring the 1 kilometer section of LaBarque Creek, which is one of the study sites from the first portion of the summer. It is an incredibly biodiverse creek located near Pacific, Missouri, which supports 44 species of fish, which is an incredible array of biodiversity and cannot be found anywhere else closer to St. Louis. Now, during summer 2018, less than 1% of LaBarque's flow was groundwater, so this variable will not come into play. Now, going forward, we will establish 2 temperature standards. Whitledge et al. 2006 estimate that smallmouth bass are subject to mass loss when temperatures exceed 27 degrees Celsius. So if the mean temperatures for one day go over that line, we'll say that's an unfavorable temperature, because of course the smallmouth bass will still live, but we'd like them to grow as large as they could be, given that they are one of the main keystone species for the Missouri Ozarks. And now the next temperature standard will be the Missouri DNR's standard, who set the maximum temperature in the LaBarque Creek to be 90 degrees Fahrenheit, 32.2 degrees Celsius. So if the maximum temperatures at any point in the day go over that temperature, we will call that unacceptable temperatures. Now, why June 13, 2018? Well, June 13, 2018 was the warmest day of the year. So we will use this day to simulate the maximum yearly in-stream temperatures. So here's the interface. This is SSTemp. As you can see, there are 4 sections here: hydrology, geometry, meteorology, and then shading. Our hydrology and geometry values were set for our 1 kilometer section of LaBarque Creek. So that's latitude, segment length, width equation, and such. And the meteorology values were set, of course, for the nearest weather recording station on July 13, 2018. Vegetation values were taken from Whitledge et al. 2006, who estimated maximum vegetation of northern Ozark streams. So our first scenario, just like Groundhog Day, June 13, 2018 happens normally. The stream is fully vegetated like it was, and stream temperatures stay as they were. Now the predicted mean temperature from our model is 25.7 degrees Celsius, and our measured mean is 25.1 degrees Celsius. So very close. And actually during some back testing, I found that I back tested about 2 weeks of days leading up to July 13, and the model's average and our measured averages were lined up almost exactly perfectly. There was just a slight more variance in the model. Now, this mean temperature will be used as the inflow temperature for further simulations, as we would assume that the section of stream above our 1 kilometer will be fully vegetated. So the water coming out of that section of stream will have the same mean temperature as the rest of the fully vegetated stream. So scenario number 2, all of a sudden in our 1 kilometer section of stream, a neighborhood is developed. Vegetation close to the stream is untouched, but for the forest farther back is removed, and vegetation density drops from 90% previously to 50%. Now our predicted mean is 27.4 degrees Celsius, and our predicted max is 30.2, which is still under our unacceptable temperatures. But if you'll notice, our predicted mean is still above our unfavorable temperatures. Now, scenario number 3, total development. Now a whole city has been built up around our section of stream. Also, the banks have been bulldozed, just like this picture here, which is actually a picture of another study site, Wittenberg Creek in Steelville, Missouri, which I'm sure some of you likely know. And if you've been to Steelville and you've seen Wittenberg Creek, you know there's not a lot of vegetation density around it throughout most of the town. And so in this scenario, LaBarque Creek's vegetation density will drop to 10%, and the topographic altitude, which refers to the height of the banks, has dropped from 30 degrees to 10 degrees. Now our predicted mean temperature is 29.5 degrees Celsius, and our predicted maximum temperature is all the way at 33.5 degrees Celsius. So that's both unacceptable and unfavorable.
I believe we oh, I see Alexander signing back on. He must have dropped for a second. So let's just stand by. Hey, Alex, we see you are back on.
Yeah. All right.
No problem.
Sounds good. All right, back in. So by only 0.01 miles along our stream segment, our temperature has reached our mean stream temperatures have reached the unfavorable condition where smallmouth bass experience mass loss. And by 0.02, they have basically equilibrated. So both of our conditions are unfavorable, but only one, of course, if you'll remember, is unacceptable. So these estimates show that an estimated vegetation density of at least 61% must be maintained to prevent mean stream temperatures from exceeding 27 degrees Celsius. That's the unfavorable condition. However, to prevent the unacceptable condition, an estimated density of only 18% is required. So for final conclusions, as global temperatures continue to rise, factors influencing in-stream water temperature will become continuously more important to conservation efforts. Remotely sensed data, like our Google Earth map, may provide to collecting field data when estimating canopy cover. However, canopy cover alone does not appear to be an accurate predictor of water temperature sensitivity. Water temperature suggests that dramatic decreases in canopy cover can rapidly degrade fish habitat within a local stream. Acknowledgements. We'd like to thank Dr. Vincent Wu and Kevin Krause from St. Louis University for establishing the temperature loggers and also providing some data. Deola Packman for assisting with field work. And of course, NGRREC and the Nature Conservancy for making all of this possible. Here are some citations. And here's my poster.
Great, thanks, Alex. Well done. Sorry you got kicked off, but no problem. And I'd like to open it up for questions, and folks can kind of peruse the poster while we're doing questions. Let's take maybe 5 to 7 minutes or so for questions if anybody has any.
And I did put a link in the chat to the poster if you want to pull it up on your own computer and have a closer look or anything. So
Great. And I see Liz has a question for Alex. I don't know if you can you unmute yourself, Liz?
Yes.
All right, great. Yes.
Perfect. Nice work, Alex. That was a really interesting project. I
Thank
had
you.
a quick question for you about the groundwater component. So I'm sure, as you know, groundwater can really have a strong influence on water temperatures, especially if you have more or less groundwater kind of regulating the temperature of the stream, which you alluded to in the first part of the project. In the second part of your project, you mentioned low groundwater inputs to LaBarque, and I'm just wondering where you got that figure from. It was 1% in 2018, I think it was.
Those figures were from the Canopy lab. Dr. Vincent Wu, who I acknowledged, they have a SWOT temperature model of the stream segment of LaBarque, and their model also does groundwater and base flow, so I got the data from them.
Okay. Yeah, I was just wondering how that is calculated, but maybe kind of outside of the scope of your work.
Yeah. As far as how it was calculated, I'm not really in the know, so to speak. I mostly just work with the data.
Yeah, I'll jump in if I can. The groundwater percent, or the groundwater contribution, Liz, is just one of the components of the SWOT model, and it's estimated during model calibration. So it's not a direct measurement, but it's sort of a it's just an input to the model, and it just needs to be estimated. So it's based on, you know, minimum flows, and that's basically how it's calculated.
Right, got it. Yeah, because like I said, groundwater can have a pretty significant control, but if you have some way of modeling what the input is at a given site, it would definitely help with the riparian component.
Yeah, that was definitely something we were considering. And looking at the groundwater data, I realized that I think 13 out of the 15 sites had no significant groundwater contribution. So that sort of went out the window with those data.
Okay, thanks, Alex. Great job.
Thank you.
Alex, this is Ted. I just quickly, can you, in your part 1 where you're looking at canopy cover, can you, I know the Merrimack River has sticking with the theme of groundwater, pretty significant spring-fed component. Were you able to, do you know the location of those springs, and were they within your 1 kilometer reach, or did you see any within your 1 kilometer reach, or did you have that information?
Well, do you mean the 1 kilometer reach of LaBarque, or any of the reaches?
Well, I guess in your let's see, your sampling, your canopy cover sampling above your reach, and maybe I'm getting 2 things confused. I was thinking the Merrimack River.
Yeah, we could not do the Merrimack River because obviously to use the densiometer you have to stand in the water in the middle, and the Merrimack's a bit too big to stand in the middle of it.
Okay.
Yeah, so mostly small creeks as far as our study sites went.
I think I conflated Merrimack River and Merrimack River watershed. So sorry about that.
Oh, no problem.
Other questions for Alex?
This is Miles. I have a quick question. Alex, just kind of jumping off of Liz and Ted's comments about groundwater, I was just wondering what other coefficients you might want to add to your model going forward. I'm just thinking of, things like groundwater inputs or, recent, like maybe the past week of weather, maybe upstream canopy cover percentages, for what the reading is downstream, weather, precipitation, rain, that kind of thing. What kind of things have you guys been talking about in your lab that you might want to add to this?
Well, my biggest thing personally is just flow, like period, not groundwater flow, just the amount of water in the creek. I would think is probably the single biggest contributor to the insulation of the water temperature. And I played around and did a couple linear regressions just on my own, and I found that I believe the correlation value I got for just straight flow and temperature insulation was about 0.6. So there's that one. There's just flow, groundwater flow, and those are probably the two biggest ones I want to go for next.
This is John. I think I understand a little bit better now, Alex. I heard this a second time. So that first part with the temperature monitoring, that was all the Merrimack River, right?
It was in the Merrimack River Basin, just mostly a lot of small creeks.
Oh, okay. So I'm trying to get a feel for, this model. I mentioned last week when you did your trial run, you showed the inputs for that model, how the cubic feet per second just seems like super, super low to me, 0.009. I think it said cubic feet per second, which is a trickle. So is this model, does it have a limit maybe about the size of the creek that you could, that it would work on? I mean, it seems like if you, when you've got like that small of a water moving through a creek, it seems like these creeks would be probably flashy in terms of, when there's precipitation, it would go up pretty fast and then come back down again pretty fast. I'm just wondering how, this model, how useful, is it mainly useful for these smaller creeks like this? What would be the limit on the flow cubic feet per second? That you
I think
no.
I'm pretty sure it was designed for larger creeks because the limit is 3 significant figures or three numbers after the decimal place in terms of flow. It doesn't go any lower than that. And I do think when you get down to that low flow, obviously it's hard to call anything a steady state, which is what SS temp is. It's for steady state estimation. And I think definitely 0.009 is on the lower end, but those are the data and that is the creek. So I guess that's just how it is.
Yeah, I was just thinking that when it's that low, probably it would be more just drainage water from the landscape, whether it would be
I see.
Groundwater or just water draining out of the landscape.
Yeah, well, if it is that, you would figure the model will not be very accurate, but it was very accurate in my back testing.
Thanks.
Thank you. Welcome.
All right, I think we have time for one more question and then we can move on.
Okay, this is Danielle. I've got a question.
Go ahead.
So Alex, you talked about, that obviously in winter, there's a lower threshold on what water temperature is going to be. And you may have mentioned this and I might have missed it, but what do you attribute the poor relationship to air temperature and water temperature at the higher temperature ranges in the summer?
If you look at the regression that I had in the presentation, I don't know if I can pull it back up, but instead of going up together or going down together, the air and water temperature both just stagnate in one area. So you sort of, if you look at it, it's just a cloud of dots. And when you have, just a cloud of dots, there's no real way to pull any sort of linear relation out of them because the temperature is not really going up or down. and the water temperature is not really going up or down. They're both just staying where they are. Oh.
Yep, we hear you, Alex. So, okay. I think that's it for Alex. Thanks again, Alex. Applause from everyone, I'm sure. So, thanks again. So next, I'd like to invite Liz Hassemuller to introduce Ashley for her presentation.
Hi, everyone. I wanted to echo first some of Jason's earlier comments, thanking NGRREC for the opportunity for students to do this summer. I know everything's been very uncertain. The program's been different in the past, but I think it's been a really nice opportunity for the students to have this type of learning experience over the summer. So I just wanted to reiterate that thought that, you know, I think the students all appreciate it, and we as collaborators really appreciate being able to work with the team and do all the this type of communication where we can all get together. So to give you a little bit of background about Ashley, Ashley recently graduated from St. Louis University with a degree in environmental science. While at St. Louis University, Ashley was active in research. She was working in my research group for a year and a half, where she was focusing on soil geochemistry. And so when COVID hit in March and things had to be restructured, we ended up kind of shutting down her project. And then with NGRREC having the internship open this summer, Ashley was able to begin working on some archive samples that she had collected and do new sample collections and process additional samples while she was in the research team. Her focus this summer has been on looking at how road salts interact with soils. And so road salting is an issue where we, you know, salt the roads during the winter months to make sure that they're safe for travel. But then there's the unintended consequences of these road salts moving into stream systems as well as soils and groundwater. So Ashley was looking at what the impact of road salting was on soils where we don't have as much information on how they're transported and moved through these systems. So with that, I'll let Ashley take over and tell you more about the work that she did this summer and what her discoveries were.
Okay, I'm gonna go ahead and share my screen then. Can everyone see this okay?
Yes.
It looks good.
Yep. Okay, so I'm Ashley, and like Liz said, I'll be talking about the effect of road salt applications on physical and chemical soil characteristics. Just jumping into a little bit of background, in the United States, road salts have been used as our primary means of de-icing roadways since the 1940s. They're very popular mostly because they're quite affordable, and they are able to lower the freezing point of water, which makes it harder for roadways to freeze over in the wintertime. In the United States alone, we use about 15 million tons of road salt every year. The most common road salt that we use is sodium chloride, which very easily dissolves in water, which means it can be easily transported to soils. Soils have been shown to be able to store sodium and chloride ions for months at a time, and eventually release those ions into surface water and groundwaters. This kind of storage and release is thought to be causing increasing salinity in chloride and surface water bodies over the last 10 years. So I kind of wanted to give a little bit of background on a soil process that is very important for my project, and that's cation exchange capacity, or CEC. So essentially, soils have clay particles in them that have a negative charge on their surface. And this negative charge allows for cations, or positively charged ions, to adsorb to the surface of the clays. Most of these are plant nutrients, so it's very important for plant health that these cations are available in the soil. But in the wintertime, sodium ions come in and can knock off those plant nutrients as well as hydrogen ions. So this leads to both a decrease in plant nutrients and a loss of hydrogen in the soil, which increases the soil pH. And this kind of effect on soils is thought to cause the decline in birch trees in New York. And it's also, this mechanism is very important for the storage of sodium in the soil because it allows that soil to kind of like hang on to the sodium for extended periods of time. So the objective for my study was, oops, sorry, trying to move the little face. So the objective for my study is to collect soil samples in a high density to the road. It's a lot different from a lot of other studies. A lot of other soil studies focus on lab flushing experiments or have infrequent sampling regimes, and they also tend to have a lot fewer sampling sites than I have. I'm going to go more into my methods on the next slide, but I sample at a very high frequency as well as a high density to the road. And we're using these samples to try to quantify long-term changes in soil chemistry using organic matter, gravimetric water content, soil pH, chloride concentrations, and sodium and major cation concentrations. The sodium and major cation concentration analyses are still ongoing, so they're not going to be included in this presentation. So my field site is Rockwoods Reservation in Wildwood, Missouri. It's about 45 minutes west of St. Louis. The site features carbonate lithology, deciduous forest cover, as well as well-defined karst topography, including sinkholes, small caves, and springs. The springs at the site have been monitored for road salt contamination since 2014 by the Haslemira lab. But the most important thing to know about this site is that there's only one continuous road that runs through the reservation, leaving only one major source of road salt contamination in the wintertime. So going into a little bit of my field methods, I've been collecting monthly samples since May of 2019, so I've been working on this project for a little over a year now. Like Liz mentioned, this summer I've been working on finishing to process an archive of samples that I've collected, as well as collected new samples for May, June, and July. So this little figure up here kind of demonstrates what I mean when I say a high density to the road. So I get my first sample at 0.25 meters from the road, and then collect in a high density until 1.5 meters, and then I also collect a 13-meter sample that's to serve as my control. I collect samples at 2 sampling depths, 0 to 5 centimeters and 5 to 15 centimeters. In July, I was also able to get soil infiltration and compaction data. So for compaction, we use this Field Scout penetrometer, and for infiltration, we hammered in these little metal cylinders into the soil, filled them with water, and recorded the amount of time it took the water to infiltrate into the soil. And for lab methods, I analyzed chloride using soil extractions and analyzed them on the ion chromatograph. For pH, I used a tabletop pH meter. For soil organic matter, I used the loss on ignition method. And for gravimetric water content, we evaporated the water and sieved for rocks so we could count for their mass in the final calculation. So jumping right into my chloride results, this figure is kind of a lot to handle at first, but I'll walk you through it so it's not so overwhelming. Lost my cursor. Where is it? There it is. Okay. The x-axis is time. Y-axis is the chloride concentration. The upper portion of the graph represents the top 0 to 5 centimeter portion of the soil, and the bottom portion of the graph represents the deeper 5 to 15 portion of the soil. Each of the bars represents one of the sampling sites, with the darkest color being the site closest to the road and the lightest color being the control. So as you can see, throughout the summer non-road salting season, the chloride concentrations are consistently very low until November, which is when we had our very first road salting event, where we see slightly elevated chloride levels in the soil. Our next event is I sampled on December 23rd, and this was directly following snowmelt of the largest snowfall event we had this past winter. We accumulated 5.1 inches of snow over 3 days, so pretty substantial event for St. Louis. Yeah, so at the site closest to the road, we were seeing chloride concentrations of 388.05 milligrams per kilogram. In addition to that huge peak by the road, we saw elevated chloride levels at every site from the month prior. So then we sampled again on December 30th. This was a week later, but it was following 2 days of very heavy rain. So we wanted to see how the chloride was impacted by that rain. So going back to the site closest to the road here, we're down to 15 milligrams per kilograms, which is a 95.9% loss of chloride in just a week. The rest of the sites also decreased substantially, not quite as much as that site by the road, but still definitely a noticeable decrease. And then for January and February, which was also road salting season, we weren't able to like time our sampling to catch an event. So we're seeing slightly elevated levels of chloride, but nothing too crazy. So I just kind of wanted to compare specifically the like rate of chloride loss that I saw in my study to another study, Kincaid and Finlay in 2009, which they found 62% of chloride was lost over 4 weeks versus my 95.9% loss of chloride. So next I have my pH results, and I just wanted to take some time to explain box plots in case you're not familiar with them. So the bar in the middle represents the median value, and the box itself represents the variation in the data. So for this graph, the x-axis is the distance from the road, and the y-axis is pH. The pink box represents the summer or non-road salting season months, and the blue box represents the winter or road salting season months. So as you can see, at the site closest to the road, the winter pH is significantly higher than the pH in the summertime. I think this is because of that of sodium ions taking up those exchange sites I was talking about earlier, which is causing a leaching of hydrogen ions, which causes an increase in soil pH. So this is the same data represented in a slightly different way. The x-axis is time, y-axis is pH. The site closest to the road is represented in orange, and the blue line represents the control site. So as you can see, before road salting season, the site closest to the road consistently had a pH lower than that of the control site, until we got to our first road salting event in November, where the pH of the site closest to the road increased to match that of the control. From this point on, the pH of the site closest to the road is consistently higher than the pH of the control. One last thing I'd like to point out about this graph is that the pH levels are down to pre-road salting season values, which could indicate that the sodium has been lost from those exchange sites, but we still need the data to back that up. So I just want to talk about the implications of pH changes. So some other studies found that there's actually a decrease in soil pH in the short term, which can cause a release of toxic metals. This is usually related to the dispersal of organic matter in clays, which once those organic matter in clays are dispersed, then the metals are allowed to, or are leached into groundwater and surface waters, which then that has implications for plants, animals, and humans. So similar to my study, other long-term studies have found an increase in soil pH, which has been found to inhibit plant growth, cause higher sodium absorption rates, and decrease nutrient availability, as well as that rapid loss of hydrogen associated with an increased soil pH. So next, I kind of want to talk about some of the soil property data that I also collected, starting with soil compaction. So this graph right here is representing the soil compaction data. I took out some of the sites just to simplify the graph to make it easier to look at. So once again, the darker color represents the site closest to the road where we see the highest compaction. And then the site, the control site is the lightest color, which had the least compaction. So compaction is important because it can make soil infiltration more difficult, which you can see in this figure down here, that these sites closest to the road had much slower infiltration rates. This 1.5 meter site has a lot more vegetation than the other sites, which the roots can create pathways for the water to infiltrate into the soil, as well as it's just less disturbed either by the construction of the road or foot traffic from people, that sort of thing. Next, I wanted to talk about gravimetric water content and organic matter. So gravimetric water content was the highest closest to the road and decreased as you travel away from the road. I think this could potentially indicate that the road plays a role in transporting surface runoff to roadside soils, which of course is very important in the wintertime whenever there's road salts on the road, because that surface runoff is also going to bring those road salts with them. And then for organic matter, we see a very similar trend where it's highest nearest to the road and decreases as you travel away from the road. So again, I think the road may be playing a role in transporting leaf litter to the roadside soils, which from just like cars driving on the road, blowing leaves onto the soil, that sort of thing. So kind of just to bring everything together, I made this flow chart. So we've kind of just found that everything seems to be happening close to the road. So we have this high soil compaction by the road, leading to the slower infiltration rates. And then the slower the water moves through the soil, the longer water is retained in the soil, which is leading to that high water content. And because the water is having a hard time moving through the soil, we could also have a potential for elevated chloride concentrations. So bringing in the organic matter, we had that high organic matter closest to the road. And then we also, that high organic matter means it may be more likely for chlorination of organic matter to occur, which essentially means that that organic matter is kind of holding on to that chloride, which again could lead to the potential for elevated chloride concentrations. So while I seem to have all of these that's like ideal conditions for chloride to be stored for longer in the soil, we still saw very rapid flushing of chloride, which just kind of goes to show how easily chloride is moved with water. So just for my conclusions, we found that the soils closest to the road are the most vulnerable to the effects of road salts. We had extremely elevated chloride levels occur directly following road salting events. These levels flushed relatively quickly following heavy rain, but they remained elevated throughout the rest of the road salting season. We also found an increase in soil pH following road salting, which again, I think this indicates that sodium ions could be dominant on those soil exchange sites. But we still need that data to back up that claim. And we also think there might be this relationship between soil compaction, infiltration, gravimetric water content, and organic matter that potentially influences chloride retention times. So I just wanted to take a second to thank St. Louis University for funding this project, as well as NGRREC for providing additional funding for the summer, as well as working really hard to make this summer feel somewhat normal for all of us. I really appreciate it. I'd also like to thank my advisor, Elizabeth Hassenmuller, as well as John Sloan and Miles Corcoran from NGRREC for their guidance on this project. And I want to give a big thank you to all my fellow lab mates for your help in the field and the lab throughout the course of this project. I had a lot of coworkers give up a lot of Saturdays to come help me out in the field and in the lab. And I know weighing soil is not the most fun thing in the world, so I'm really grateful that they took the time to help me, and I wanted to thank them for that. So thank you for listening, and if you have any questions, I'd be happy to answer them.
Great. Thanks, Ashley. And we have some time for questions, so fire away.
Oh, should I pull up my poster?
Yeah, that would be great.
And I'm grabbing the link right now too to share in the chat. There you go.
Yeah, Justin has a question. Go ahead, Justin, if you'd like.
Yeah, thanks, Ashley. Great job. I had a question. I went to a conference last summer, and this was like actually a symposium. They're talking about road salt and that sort of thing. And I know out west, like in the states of Montana, they deal with this quite a bit up there. I mean, it sounded like they had some alternatives, or I was wondering if you knew of anything in the Midwest, if there's, this is probably the most effective in terms of de-icing the road, but are they do you know if they're exploring any alternatives in this region?
I'm not totally certain. I think I've heard another one of our field sites from Liz's lab is Litzinger Road Ecology Center, and I remember talking to the people that work in the office there one time about them using beet juice on the road that runs along there. I know nothing about it or how it affects soils or water or anything like that, but I do know that that's an option that's being explored as like an alternative to traditional road salts.
Okay, thank you.
Did you say beet juice, Ashley?
Yeah, beet juice.
Okay.
I have no idea how it works. I probably should look into it considering I've been researching this, but yeah.
Well, is there another salt? So the sodium chloride, which is a salt. Are there other salts that are used?
Yeah, I think farther up north they primarily use calcium chloride because it lowers the freezing point of water even more, but it's more expensive than sodium chloride. So like in the like around here, you know, we don't get that much snow, so it's not really necessary for us to use it. And there have been some studies on the effects of those salts on water and soils as well, I think. Yeah.
This is Liz, just to dovetail on some of the things that Ashley was talking about. Danielle actually recently wrote a paper looking at brining as an option for reducing the amount of road salt contamination, where they mix salt with water and then spread that to reduce the overall load of sodium chloride. And as Ashley mentioned, with some of these other types of salt that are out there, like calcium chloride or magnesium chloride, they're pretty expensive and they don't really reduce the issue of chloride contamination because they all contain chloride.
Right, so that's what I was thinking. So and I know that Ashley's going to become a soil scientist, so I'm going to quiz her a little bit more about soils. So calcium chloride is of course well, calcium of course is a divalent cation versus sodium, which is a monovalent. Do you know? Can you speculate, or do you have any feeling at all for what that might mean in terms of the impact on the soil?
I'm really not sure. I haven't done a ton of research on it. I'm not sure if because calcium has a higher charge, I'm not sure if that would mean it has like a stronger bonds to the clay in the soil. So maybe that would stick around even longer. But I'm really not sure.
Yeah, that's good. Yeah, calcium's divalent. It would cause the soil, help the soil particles cling together instead of sodium, which causes them to disperse. Yeah, when you're looking at soil, so if you're working with agricultural lands and irrigation water, that's a big one. So yeah, that was good. You're right on there. It has a higher charge density. Thanks.
Still have a few minutes if anybody has more questions.
Hey, this is Danielle. I've got a question. You mentioned a prior study that was done, I think it was like 10 or 15 years ago, where they found that there was a much higher retention in their soils that over the course of like 4 weeks. And what aspect of either the study or of the soils do you think had the greatest influence on the amount of retention?
I've actually thought a decent amount about this question. I think it might be that study that I referenced earlier was a lab flushing experiment. So I think maybe the like very controlled environment that the soils are being tested in is obviously very different from having soils out in the field and the natural environment where I have no control on a lot of things. So I think that could potentially be contributing to the very different amount of the chloride loss, sorry. But also that they had like a controlled amount of water entering the soil. It's kind of the same idea, but we can't control the amount of rainfall that falls into the soil. So, you know, we had no idea that it was going to rain. We just kind of got lucky that happened and we were able to get this interesting data. It was never intended to be part of the study. We were just going to see how it declined over time, but we just happened to have that really interesting event happen. So yeah, I guess overall, I think that maybe it's due to it being a lab experiment versus a field experiment, just because we can't control a lot of the variables.
Okay, thanks.
Thank you.
I've got a question. This is Ted. I'm not a soil scientist. I know very little about soil sampling, but your time series of chloride concentrations is interesting. And the fact, you mentioned the fact that you caught an event. Is there a method that you could potentially in the future deploy that would give you a little more high resolution time series other than just intermittent grab samples that obviously have some limitation?
Yeah, I don't really know. I mean, it's a thing that my advisor and I have thought a lot about, and we kind of designed this project to kind of try to do that a little bit more than some other studies. But with soil sampling, it's just like such a field intensive thing to do that you really can't do it much more frequently than I did. Unless you have like 100 people working for you in the lab or something. But yeah, I don't really know. I know one of our grad students in the lab did a project using lysimeters, looking at the pore water in the soil, which I think she could sample at a higher frequency. And I think that produced some pretty interesting results, very much related to this type of project. Just focusing on the water instead of the soil.
Great, thanks.
Yeah.
Were you thinking, Ted, like about sensors you could put in place?
Well, that was one question. If there's a sensor, or I was thinking, actually, I was thinking of measuring the water. So if you had a way to have a well or something like that.
You'll learn about TDR probably, actually, and other ways to monitor soil moisture in situ. That time domain refractometry, and there's some other methods that are in probes. You put them in the ground, and you can either leave them or you put them in there and take a reading. You'll learn about those.
Okay, cool. Thank you.
All right, I think we have time for one more question if anybody has anything. All right, if not, we will move on. So big round of applause virtually for Ashley. Thanks again, Ashley.
Thank you.
And we will move on. Justin Shu will introduce Phil here for our last presentation of the day. So
right.
Thanks, Justin.
Ted.
Thanks.
Yeah, thanks, Ted. I think most everyone knows me. There might be a couple names on there I don't recognize, but for those that don't, my name is Justin Shu. I'm the Conservation Program Manager at the National Great Rivers Research and Education Center, also a wildlife ecologist by training. So I'm pleased to announce Phil was my student this year, and he is a Lewis and Clark Community College student in the Restoration Ecology program. He is going to be completing his final semester this fall. It's been kind of, I think, neat for him because he has worked with our Habitat Strike team, actually doing some of the management. So a lot of the things I'm interested in is wildlife response to management, vegetation, sometimes getting into multi-scale questions with GIS layers as well. But yeah, he's actually helped our strike team, and he's kind of helping push the needle on some previous research from interns I've advised in the past. So it's really happy to get him a part of this project, and I'll just let him tell you about it. So take it away, Phil.
All right, thank you, Justin. Let me just share my screen real quick. All right. Okay, as Justin said, I'm a student at Lewis and Clark Community College. I'm in their Restoration Ecology program. I've also previously worked as an intern for the Habitat Strike team, doing a lot of vegetative management. So first, I'd like to just go over what the strike team is. So the main purpose of the Habitat Strike Team is to improve wildlife habitat through vegetative management. And we do this mainly through prescribed fire, herbicide application, and timber stand improvement. With prescribed fire, we're mainly just we use that to get rid of invasive species such as honeysuckle, and with the prescribed fire, it also promotes native plant growth. Then another tool we use is herbicide application. We do this primarily through backpack spraying, and we're mainly spraying bush honeysuckle and other invasive species. And then timber stand improvement is where we remove undesirable trees in woodlands, and we're doing that mainly to promote the establishment of oak hickory forest communities. And here you can see some pictures I've taken while on the job. That's actually me right there, and that's a cedar tree I had cut down, so just letting you guys know about that. So I like to talk a little briefly about bush honeysuckle, which is the primary antagonist of this study, if you will. So it's an invasive species. It's native to Central Asia. It prefers a temperate climate. That's partly why it's doing so well here in North America. And it was introduced in the late 1800s to America for erosion control and wildlife habitat. It has since invaded most of the eastern and Midwest United States. It outcompetes native understory and midstory plants, and it does this by, it leaves out earlier than our native plants here, and that gives it a much a better advantage as opposed to the other native plants. And it also creates a lot of shade, and so that shade doesn't allow for the native plants to grow. So, and it also, most wildlife does not really consider it to be food. So it's pretty much just taking up a lot of space and not really doing anything for our forest communities. So the objective of the study was to determine the effects of bush honeysuckle on avian species of greatest conservation need. So these are species that have been designated by the Illinois Wildlife Action Plan. They are bird species that are in steep decline, have low population numbers, or are otherwise threatened or endangered species. And we're also trying to determine the effects honeysuckle has on the richness and abundance of these species of greatest conservation need. So richness is, it is the amount of species per given area, and abundance is the amount of individuals per species population in a given area. So for this study, I chose these 3 birds to focus on. They are all species of greatest conservation need. I chose them due to their nesting habits. So the eastern wood pewee nests in the upper canopy of the forest. The Acadian flycatcher nests in the mid-story layer of the forest, and the eastern towhee nests in the ground level. So these 3 species are a good way to measure the effects bush honeysuckle is having on these populations. So here we just have an overall layout of where the study takes place. It goes all the way down to Pierre Marquette State Park right there, and then all the way up to Arlenville and some other sites around there. So we have 2 sites, Pierre Marquette and Beaver Dam. Those are both state parks, but the rest of these sites are all actually private land. So we have done a lot of research and management on these private lands, and it's been a very rewarding experience for us and the landowners, and we very much appreciate their cooperation. So for collecting the avian data, I personally was not a part of this. This was previous interns. So there were 52 point count stations across 22 sites, and there was a 5-minute survey at each site. And they visited these sites twice a year. And then the survey was usually conducted from sunrise until 10 a.m. And this was all done in the breeding season, so June. So what they would do at each survey, they would listen for different bird calls within a 100-meter distance, and they were listening for birds such as blue jays, robins, cardinals, as well as listening for these species of greatest conservation need. So for the vegetative data collection, they took the average of 4 random vegetative plots per point count station. These were 40 meter squared plots, and they were measuring the canopy cover, the bush honeysuckle coverage, and the amount of stems, the multiflora rose coverage, which is another prominent invasive species in the area, and the overstory and understory species. And then in the southeast corner of each plot, they would measure the vascular flora less than a meter in height, and then the bush honeysuckle stems and coverage, and multiflora coverage, as well as taking a look at the bare ground and leaf litter percentage. So this is where I come in. Originally, I was planning to do more field work, but due to restrictions from the coronavirus, we were forced to forego any field work. So I was kind of put into, I guess you could say, an uncomfortable situation for me, because I've been more focused on getting the field work done. But overall, this has been a very valuable experience for me, learning how to analyze and enter the data. So I would do this by entering the data through Google Sheets, which is just another form of Excel for those of you that don't know. So my boss would, Justin Chu, would send me these data sheets, and I would look at them and sometimes have trouble deciphering Justin's handwriting, but overall it was a pretty easy time for me. So I would look at the data sheets and I would enter that data into the Excel file for all of this data where it's all collected. And I would then create scatter charts in Google Sheets to help better visualize the data and get a better idea of the effect honeysuckle is having on these avian populations. We also utilized a linear regression to determine if the honeysuckle was a significant predictor of avian response. So here's the first chart. This is the effect bush honeysuckle has on overall cumulative avian richness. So that means the overall species of bird in the area. So that's including cardinals, robins, as well as the species of Gray's conservation need. So you can see that there is a slight negative trend here. Although I have to preface that it is a very slight trend at the moment, though it is still where there is a presence of bush honeysuckle, there are less avian species documented. These graphs are very similar. This is the looking at the richness and abundance of these species of Gray's conservation need. Once again, richness refers to the amount of species per given area, and abundance refers to the amount of individuals of each species per given area. So once again, it's showing a slight negative trend. So overall, when honeysuckle is present, there's a downward trend in the abundance and richness of these species. And here we're going to look at the 3 species I chose earlier. The Acadian flycatcher is there in blue, the eastern towhee is there in red, and the eastern woodland pewee is in yellow. So first you'll notice that the towhee and the Acadian flycatcher are experiencing a negative trend here, once again, and that is likely due to the fact that they nest in the lower and mid-story layer of the forest canopy, and that is where bush honeysuckle primarily inhabits, so their nesting sites are affected by that. And then you can see that the eastern wood pewee is actually experiencing a positive trend, and that's likely due to it not being affected by the presence of bush honeysuckle and perhaps lack of competition between the other species that are in decline. So overall, in general, we found where there is honeysuckle presence, there are less species of greatest conservation need documented. But with the current data set, we cannot discern a significant relationship between bush honeysuckle and avian response. So that leads me to the management implications and future direction of the study. So even though the trends are very slight, we still notice that there are less species being documented around these bush honeysuckle infested sites. So it is still beneficial to remove the honeysuckle. And to further increase the study, we'd like to just overall increase the scope of it. Right now, the current data we have is the sites are very, it's a very narrow view of the data and this conflict between honeysuckle and avian species. And so by increasing the scope, we might look at sites with a much denser concentration of bush honeysuckle, because a lot of the sites that we looked at were not as inundated with honeysuckle. And we would also like to quantify the management through ArcGIS mapping software, and this would be done through this app called Collector. The strike team uses it. It's essentially an app where it tracks the movement of the workers and therefore it tracks the management being done. So it tracks like the backpack spraying where the herbicide is applied, and also it tracks like prescribed fire and other management practices like that. So thank you all for listening. I'd like to first thank Justin Shu for helping me along this process. It's been very challenging for me because data analysis and entry hasn't really been my forte, I guess you'd say. I'd also like to thank the Habitat Strike team, Lindsay Griggs and Cody Berry. They've helped me a lot in learning how to implement these management practices. And then I'd also like to thank the previous interns, Maddie Lieberman, Kai Hardy, Summer Wolf, and Lucas Goldschmidt. They all essentially collected all of the data and did some analysis on it, and without them, I wouldn't have been able to complete this project. I'd also like to thank Illinois Recreational Access Program, the Illinois Department of Natural Resources, and Lewis and Clark Community College for educating me and giving me the tools necessary to pursue this study and this career. And I'd also like to thank the private landowners for their cooperation in this study. So with that, I will leave it open to questions.
Great, thanks, Phil. Well done, and round of applause for you. We have plenty of time for questions. I'm going to start off with one right off the bat, as your poster is up here. So I have, my question is, what do you think are some of the limitations, or maybe, a couple of the limitations of your study, and what do you think would help with making your trends maybe more clear if you were to add some components?
Yeah, so I understand that part might be a little bit confusing, but so to increase to remove some of the limitations, we might essentially, like I said, increase the scope of the study. So we'd be looking for sites with a higher bush honeysuckle percentage, because a lot of the sites we looked at had a pretty significant presence of honeysuckle, but there is definitely some sites out there where it's much heavier, and looking at those sites might give us some more insight and probably add to the current data set we already have, and and show a much more negative trend than the slight one we have at the moment.
Great, thanks. So one other question I have is, did your data look at the size of the habitat that you were, where your point counts were?
Yeah, so that's partly where like ArcGIS would come in handy, mapping out the plots. But yeah, early on, we were also trying to maybe look at the effects of habitat fragmentation and how like a lot of these sites are by either like agricultural land or maybe even some urban areas or suburban areas. So yeah, we were mostly looking at it from like the size of this habitat might be a good thing to do in the future studies, because a lot of these habitats are quite fragmented. So that could play a considerable effect of the spread of honeysuckle and other factors like that.
Thanks. I see Tony Dell has questions. Tony, go ahead.
Yeah, hey, thanks, Phil. It was really interesting. I've got a couple of kids running in and out, so I hope I didn't miss it. And you did talk about it, but are you able to look at your data and see if there's any effect of functional group? So whether predators might be different than insectivores, just the birds that you look at. I know you didn't have a massive species diversity, but you do have some functional diversity in there, I imagine.
Yeah, we were, yeah, we didn't really
Was
look
that
at
clear?
we weren't really looking at the, we're mainly just focusing on the species of Gray's conservation need. And I did do a bit of research throughout the study on like, there was a study I looked at where it looked at how honeysuckle might become an ecological trap for these bird species, in that while a lot of bird species will nest in bush honeysuckle, but it kind of limits their, it kind of makes them more open to predation from a lot of other animals because of, I guess, just the structure of honeysuckle and how it's not as good, like, I guess, as well camouflaged or other factors like that. So it leaves them much more vulnerable. And for some birds like robins and crows and other like generalist type birds, it might actually be more beneficial to their populations because they just have a much higher number. But when it comes to these species of Gray's conservation need, they're probably much more vulnerable to steeper population declines.
Got it. Thanks, and congrats.
Thank you.
All right, Dave, I see a question from you.
Hi, yes, Phil, thanks for the talk. And I have just a couple questions. First is just a conceptual question. What did you come across anything in the literature about the ecology of these species that would make you predict that these honeysuckle would even have an effect on the animals?
So, like when I chose these 3 different species, I like for the eastern towhee, for instance, that guy right there, they nest closer to the ground, and same with the Acadian flycatchers, they nest in the lower to mid-story layer of the woods. So that's where honeysuckle primarily occupies. So it creates a much more, it limits a lot of their nesting habits, or puts their nesting habits in more danger, I guess, from predation, like I mentioned. But then there's species like the eastern wood pewee, which nests high up in the canopy, and they're largely unaffected by its presence.
Okay. All right. Yeah, that makes sense then. And then my second question was just looking at your figure in the poster here. And I think you mentioned this, your coverage of different proportions of honeysuckle cover wasn't so broad. So just looking at the data, it seems really patchy in that you have some sites that either had no or very little honeysuckle, and some that had almost half of it was covered with honeysuckle. So I wondered whether you ever considered in your models just breaking it down into classes instead of like a percentage cover, and seeing if maybe there would be differences based on that. I mean, looking at the data, it doesn't seem to be, but you know, it just could be one other way of looking at your data, if that makes sense.
Yeah, I think that would play into more about just kind of increasing the scope of this study, because like you said, the site's honeysuckle presence was very unpredictable, I guess. It was very all over the place. So with future study, we might kind of fill in some of those gaps with sites with a lot more honeysuckle presence, and then sites with not as significant of a honeysuckle presence, just to get a broader idea of how it's affecting the avian species.
Thank you.
Ashley, looks like you have a question. Go ahead.
Yeah, I just kind of had a very basic question. I was wondering, like, so if someone has like honeysuckle growing in their backyard, is there something they can do to help with that, or is there anything that they should do to help get rid of it? I was just wondering your opinion on that.
Well, my opinion would be to just get rid of it. You can, I know a lot of you probably don't want to just go out and use like glyphosate, which is the chemical we use, but I've heard there are some homebrew like recipes you can make just to get rid of it. I'm not too familiar with those, but I know they do exist. And basically, you just want to get some loppers, depending on the size, maybe even have maybe someone you know, or if you know how to use a chainsaw, just to cut it out and then spray the stump with it. But also just depends on like how much honeysuckle there is. But definitely find a way to get rid of it, because it's very bad for our local woodland communities.
Okay, thank you.
Yep.
John Sloan typed a question mark, so I presume that means he has a question. John, go ahead.
Dave has one before I do.
Dave, do you have another question, or are you done, Dave?
Oh, did he ask his question?
He did, yeah.
Okay, he was before. Okay, sorry. It's all after answering. Well, my question, I guess, is so they got this data in 2018. I mean, do you have any indication of how the number of birds they measured in 2018 would have compared to like previous years? I think you said in the introduction, maybe are these species that are declining already, or?
Yeah, there's species that have been, I think, like the start date of when they started like taking notice of their decline was around, I want to say around 2000, like when the Illinois Wildlife Action Plan started like taking notice of these. Justin might know more about like the date that it actually started, but yes, these species are species that have been in decline and decreasing in population numbers since probably since before 2000, but that's when they started really looking at it, I think.
Okay. And then bush honeysuckle, you might have said this, but how does it, what causes it to, what's the mechanism for its dispersal? Why has it spread out so quickly?
So there's a lot of answers for that. But from the research I've done, just to kind of understand honeysuckle better, I think when it started, at first a lot of people started planting it. I think it started in New York for erosion control, and then also for habitat. They thought it would be good habitat for wildlife, which is proven to be the opposite. But another, besides like just people spreading it around, another main mechanism for its spread has been just avian spread through avian, like spreading the seeds through like just the natural way that birds spread seeds.
So some birds eat the fruit of the bush honeysuckle?
Man, this is where I probably should have done some more research, but I'm sure there are some species that do, but when it comes to, Justin will probably know more about this as well, but I think I did mention that not a lot of wildlife considers it food, but I think some generalist species like robins and whatnot might probably try and eat the berries on it, but I'm not too sure about that.
Yeah, I just, when I was a kid on our farm, you never saw it, and now that I'm older than a kid, it's just all over the place.
Yeah, it's everywhere.
It's spread, yeah. So anyway,
Once you,
Phil, I was happy. Phil was one of my soil students. I'm happy to see you were able to do an internship. That was great.
Thank you.
I have a comment about bush honeysuckle. Does anyone on the phone, and I'll look at Justin or Dick or Phil on this one. I believe some departments of natural resources decades ago would sell bush honeysuckle as an erosion control shrub, some other or wildlife food. Is that true?
That's true.
Okay, yeah.
It's one of several of those kinds of things that have become regrettable decades later.
You can yank it out by hand. I'm not sure how it helps control erosion. As long as you get it when it's young, you can just yank the stuff right out of the ground.
Yeah, but we've also seen some real, like 20-year-old honeysuckle that are about, I'm gonna say like 25 feet tall. Those guys are pretty much trees at that point.
Yeah.
Those are a lot more difficult to deal with.
All right. Other questions?
I have one more.
Go ahead, John.
When you cut that cedar tree down, I noticed you cut it up about 3 feet, 3 feet off the ground. Is that something on purpose, or?
That was, if I recall, when I kind of first started off, so I was being a lot more cautious, and I didn't show it, but in the picture behind me, that was actually at Pierre Marquette State Park. And so there was a Pierre Marquette cabin directly behind me. So I was being very careful not to have that tree fall on that cabin. So
Yeah, that was a big tree, yeah.
Yeah.
Okay. John, any more questions from you?
Well, yeah.
Oh, hit us.
So when they measured the songs, they did it, any bird that you could hear within 100 meters. And I would just, is that just kind of how far the sound goes? Or obviously you can't measure out or is that just how they define it? If you hear a bird, you assume it's within 100 meters?
Well, so yeah, I wasn't a part of that. So I guess Justin might be able to better answer that. But I think, I guess there was a way they could tell based on probably just, I guess, the echo, but I'm not really sure. But I assume they probably just, if they heard it, they probably, I guess, counted it, because probably, if they could hear it, it was probably close enough. But I'm not too sure on that, because I wasn't able to do any of that, unfortunately.
Thanks.
Yep.
All right. Well, I think that wraps it up. Quick year this year for the internship symposium. So congratulations once again to all 3 students. Thanks very much for your hard work over the summer. Very much appreciate your presentations. Well done to all. And we encourage you to keep in touch with us here at NGRREC. Good luck for the rest of your summer and beyond. So thanks again, everyone. And with that, I think we'll wrap up.